Okay, welcome to the second class meeting of EECE341, Introduction to Communication Systems. Since this is the period for add drop, I may spend some time to repeatedly tell you the course administration. So the most important thing is your attendance, because up to 1/4 of the class meetings, you can just skip even without notifying me. Okay, so I'm very generous in that sense. You can just do not need to appear here up to as far as our school regulation allows. No penalty at all. Okay. However, if you cross the line, then I can't do anything according to the school regulations. So be careful. So please regularly check the post-tech electronic attendance system. So if you haven't yet officially enrolled in this course, but you appear here today, then come to me after the class meeting and say that my name is blah, 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 and I'm here. Then after you add, probably your attendance will be marked as absent. I will change that. Got it? Also, homework, quiz, exam, and voluntary project, the last one of which I will tell you after the midterm. But you can find it from our secondary homepage, which is linked to my lab homepage. So you go to this link, especially schedule and download, and you can download all the handouts. They are all password protected because the materials are copyrighted materials. The publishers allows us, the instructors, to use their figures from the textbook without problem. However, it is not good to upload it, so I put the password. However, as you've seen already, if the handout is for chapter 1, then the password is ONE in a lower case. Got it? Homework 1 is already assigned, as I told you, and sometimes I will assign that kind of homework in order to check whether you are regularly study the course material. The homeworks are usually very easy, and sometimes what I have found so far is that some students just do something else in the class meeting, and what they do is that if I post the homework, then they view the YouTube video class meeting and try to find the answers to the questions in the homework, something like that. That is recommended actually. You can save a lot of time. For example, you cannot just understand my English, my poor English. In that case, what you can do is that you do something else here, just to see what happens, and do, for example, homework for circuits course, and you go to the dorm and view the class meeting, and the speed may be up to your choice. It may be 1.75 times the ordinary speed, or it could be 0.5, depending on your English proficiency. So I'm kind of generous in the case as far as you do not annoy me during the class meeting. Got it? So homework 1 is assigned and available from PLMS, and it's due just before next Monday class meeting. Usually I give 1 week, so 1 week or less than 1 week. So be careful. The due depends on the situation. Sometimes the due is just the next day. For example, I give the homework on Monday and the due is Wednesday in the same week. Quiz 1 is already announced last time, and I told you that it will cover the prerequisite material, signal gen systems, especially Fourier series and Fourier transform, continuous time, and possibly discrete time. I'm not yet decided. I will cover the discrete time Fourier transform, but definitely continuous time Fourier series and transform will appear in the first quiz. And it will take around 30 minutes in our 5th class meeting. Okay. By the way, about the course material, about the help, you can approach the tutor. as I have already sent you the messages, our announcement have a link from the message of our tutor. So try to utilize our course tutor as far as possible. About the information theory, I found that this course is in the exactly same time in other classrooms. So you may not take it both of the classes. I'm sorry about that. Okay, last class meetings video is already available from our YouTube channel, so you can view it. I've checked any incorrect statement and I didn't find, so it seems okay. So here goes the brief overview of this course. Again, we are covering the chapter 1, and there will be signals and systems part. I will talk about that very quickly next week for only 2 class meetings. Of course, I cannot cover all the material about Fourier series and transforms, so you have to study yourself to prepare for the quiz. And then we'll talk about so-called linear modulation techniques and some nonlinear modulation techniques. And we will study the notion of multiplexing. And then, so this part is mostly analog communications. And even though it's just 2 chapters, I may spend a lot of time because usually introductory communication systems course covers analog communications more than 2/3 of the entire semester. And then I will talk about digital communications, which is offered in a separate course. Probably it will be offered in the next semester, spring 25. I'm not sure who will teach, but I may teach again. Okay, I'm not sure. We haven't yet decided. So some of you are very kind of cursed generation of post-tech EE who takes Professor Cho's course more than 2 or 3 times. Once there was a kind of cursed generation who took my course 3 times, and you may kind of reach that record. And also a blessed generation who didn't take any course from me because I was in sabbatical leave, blah, blah, blah. Anyway. And I promised last time that I will definitely cover the last chapter because I believe that it's very important for you to be exposed to the theory of information theory as early as possible, because it gives you a chance to understand how electrical engineers handle information and how we measure the amount of information in a message mathematically. So that is very important part. So if I cannot cover all the digital communications parts in detail, I will definitely cover at least mention this information theory for more than a week or 2 weeks. Got it? Because I can cover or we can cover digital communications in a separate course. Okay, here goes the review of last class meeting. So the most important question is not only related to this course, is that why we communicate. Why do we need to communicate? And the answer you already know who paid attention to the last class meeting or who tried to solve the first homework problem. What? Imbalance of information. If information you have and I have are the same, especially about, for example, this EECE341, why do you take it, right? So one of the reasons why you take this course is that amount of information on this topic is different in your brain and in my brain. So imbalance or difference in amount of information of information motivates us to communicate. You need to remember that, okay? And of course, there are limitations in every communication, especially since we are living in this physical world, we are limited in space and time. And that is very good dimensions we need to remember whenever we do something, space and time. That's very important. And also, one of the keyword is that even though I didn't mention, last time, in the last class meeting, what I mentioned about communication was all about pre-electrical communications era. And from today's lecture, we will all talk about electrical communications. So in the last class meeting, I talked about Stentor, a hero, a very not well-known hero appearing in Iliad of Homer, whose voice was very loud. And you also know some story about Archimedes. When Romans invaded Greece, he used some shield to reflect the sunlight. Of course, they also used the sunlight to communicate the signals at that time, but they were all limited to a short distance communication. And also, amount of information that could be conveyed was very limited. So they wanted the long distance communication, which means that you have to consider very large distance. The problem is that usually it takes a lot of time. For example, for a pigeon to fly or a horse to run over the entire route. So the ancient Chinese people invented this network called Pabal system in Korean. So it's kind of the Bonghua system. So Bongsu system. Bongsu means that Bong means fire and Su means smoke. Okay, so they used fire and smoke to convey some information. And interesting thing is that when I looked at Wikipedia, from the southern part of China to Beijing, for example, in Ming Dynasty or Qing Dynasty, when they used this signal fire and smoke system, they could convey the message just within 3 or 4 hours from the most southern part of their system to Beijing. And it's more than some 1,000 kilometers. So this system was very, very fast. So it could cover a very long distance. The problem was that there were only, in Joseon Dynasty case, there were only 5 chimneys. So mathematically, they could send 2 raised to the power of 5, which is 32 different messages. However, as I told you, in order to reduce, not completely remove, in order to reduce any message error, they decided not to utilize every possible 32 different message. They limited their message to 5. You remember the figure, right? So they even implemented a rudimentary forward error correction method. So remember this, ancient people were not dumb. They were very, very clever as us, but their tools was very limited. In their toolbox, there was very elementary tools only. Now, as electrical engineers, we have a lot. Remember that. Anyway, this part, I didn't mention, but it's also very important. For example, suppose in order to cover long distance, you use pigeon. You know that, 비둘기, right? On the leg, they usually use a very small paper, right? And rolled and put in a straw type message box. And what was the problem of pigeon? They are not that clever. The pigeons are not that clever. So the message could be received by enemy or unwanted receiver. So what do they do? What did they do? They encrypted the message, right? So this encryption for secure communication started from the earliest long short distance communication. I talked about Stentor, right? Move forward. Sometimes the enemies will listen to the Stentor's voice and they may change their strategy. So probably they encoded like this, right? Okay, if I say this time, if I say move forward, it's backward. Move right, then left. and they change after 3 hours. Or if they listen some very loud sound, then they change, something like that. Anyway, secure communication is also a very important topic. And interestingly, information theory covers that part, information theoretically. Some of you are from computer science and engineering department, and you know that the currently modern encryption system is based on the factoring very large numbers using prime numbers. But this security or secure communication, information theoretic security is different from that. It's all statistical. So you may have some interest in it, but their application is currently a little bit limited. However, as far as I'm concerned, what I believe is like this. Probably you've heard that there's some quantum computer that is very fast, may solve every possible encryption. Actually, that is not correct. If we encrypt information theoretically using some statistical encryption method, we can still beat quantum computers. So as far as current RSA-based encryption system can be broken, this information theoretic encryption cannot easily broken. So that's kind of one of the reasons you may have interest in information theory. Another one is this one. So you cannot put a lot of things in a very small paper when you use Pigeon. So what they do, for example, you want to say that I love you, but what you do is that you remove all the vowels except I. So I, L, V, Y. Then your lover in the other side may read the message in the message conveyed by Pigeon and smile, right? So compression is also very important in communication. That topic is also covered by information theory. Okay, so information theory is very, very interesting topic, even though it is not usually taught to undergraduate students. But what I personally believe is that you can take the our graduate level information theory course as far as you have taken EECE342 전자수학 A and love the probabilistic modeling of uncertainty. Anyway, so I will talk about that at the end of the semester. Now here goes the preview. So we are going to cover a brief history of electrical communications. This is very important term, electrical communications, because that kind of differentiates me in the Department of Electrical Engineering or Professor Kim in Department of Humanities. Probably some of you have taken some elective courses from our humanities departments talking about media or newspapers or SNS, something like that from Professor Kim. Anyway, so I will talk about electrical communications. And today I hope we will cover all the important kind of landmarks in the history of electrical communications. And you may have, at the end of today's class meeting, you will have your own lessons. So this is also an important keyword. Whenever you experience something, whether it's taking a course or sitting in a single class meeting or do some extracurricular activities, every time after you finish some activity, try to find a lesson or lessons from those activities and try to make it a habit of your habit. And then you try to find something important. And sometimes that changes you in a better way every time you experience something. And as an electrical engineer, probably many of you may not become electrical communications engineer. However, from the history of electrical communications, I hope you have your own interesting lessons about how electrical engineering changed or shaped the world and what kind of direction the electrical engineering is moving. Okay? Anyway, I will cover this part very quickly. So, purpose of this course is about all about electrical communications. And as the last line says that, it started from the equipment called telegraph in early 1800s. So this is the table from our textbook, and I highlighted some important years. And you know, the Volta, the French guy, I believe, kind of invented Volta, invented the battery. Yeah. And from that event, many people could do their own experiment, some electrical system experiment. Some people considered, for example, Galvani used the leg of a frog to understand what kind of thing is stimulating the people's muscles, something like that. And immediately, almost immediately after this battery is invented, people started to think about using this battery to convey a message. Even though many small historic events are not there, but immediately after the invention of the battery, people started to use short distance communication. For example, I can connect a wire to your leg, and I may have a switch here, and I can push the button. For example, if I push the button connected to your right leg, then the message says, wake up. Okay. If I push the button connected to your left leg, then you can just skip this part, something like that. And actually, almost the same thing they did. They didn't have computer, they didn't have touch screen, but only battery and wire and simple switch. They could do some short length distance communications. But what was one of the most important inventions was so-called Morse code, associated with telegraph or telegram. And it was around now 200 years ago, less than 200 years ago, right? See that? Here, in 1864, Maxwell kind of not invented the four equations, but kind of systemized equations about electricity and magnetism. And the Maxwell's four equations actually are not provided or presented by Maxwell. As some of you already know, Heaviside kind of reorganized all the equations what Maxwell provided. So actually, some people say Maxwell Heaviside four equations. By the way, some of you may not only use Maxwell's four equations. As an electrical engineer, what you have to remember is 5 equations related to electromagnetism. And what is the last one except the Maxwell's four equations? What do you need to remember? That is Lorentzian force. You remember that? So this equation is called Lorentzian force equation, right? And this equation is very important because now probably you realize that Maxwell's four equations has no physical quantity called force. It's all about just electrical field and magnetic field, right? Electric field and magnetic field. But by using that, if we want to operate our electric motor, what do we need? We need to exert some force, right? So Maxwell's four equations and Lorentzian force equation consists comprises the most important equations for electrical engineering. And some of you may say that, wait a minute, professor, in signal-gen systems, no one talked about Maxwell's equations. And some of you are taking this course, retaking this course, and remember that professor never mentioned Maxwell's equations, even though it is a course for communications that use mostly electromagnetic wave. One of the reasons is that even though we are based on 5 equations, depending on the scale of our electrical system or our behavior of electrical current or voltage, sometimes we can make a very, very good approximation. And then, for example, communications engineers like me lives in this approximation without using Maxwell Heaviside for equations, even Lorentzian force. Anyway, so Maxwell kind of make the theory of electromagnetism. Sorry. What is wrong? Just a second. Okay. I'm sorry. So Maxwell also derived some interesting result. What was that? He predicted existence of a wave called electromagnetic wave. So Maxwell kind of sorted out a lot of incomplete equations into very simple, probably 17 or 19 equations at that time. But also, he combined some of his equations to predict the existence of a wave. What he did was that while he was manipulating with differential equations, he could get a so-called an equation that can be categorized as a wave equation. And probably you remember, right? Some partial differentiation with respect to time and space combined, then that kind of equation is called wave equations. So he predicted, not only predicted the existence of so-called electromagnetic wave, but also from the well-known that because the wave equation was exhaustively researched already, he could even predict the speed of that electromagnetic wave. And that was very fast. So far, Maxwell just provided some interesting prediction and reorganized everything. And now you have to understand, you have some lessons. From here to there, how many years? 30 years around, right? During the 30 years, a lot of engineers, now we can categorize them, a lot of engineers try to use this electromagnetic wave to replace the telegram. They renamed the telegram as wired telegram. And they wanted to invent wireless telegram. And actually, it didn't take longer than 30 years because at that time, Marconi patented entire complete telegraph or wireless telegram system, but that invention was already going on before this patent. Some of you know Rutherford, who discovered the existence of the nucleus in our material by shooting some alpha particle to, was it gold sheet or something like that? And actually, Rutherford, even though he was a very promising physicist, when he heard about Maxwell's prediction and Heinrich Hertz demonstration of existence of the electromagnetic wave, he actually temporarily shifted his interest to wireless communication. And even he wrote some research papers on radio communication. But Marconi, Guglielmo, actually they say that Guglielmo, I don't know why this L is missed, but Guglielmo Marconi was an amazing guy. He was very, very productive. And he kind of was a very, how to say, he was a kind of showman. Probably some of you know the Steve Jobs of Apple. And he was a very good presenter. And he was a very good, how to say that, present entertainer. But you have to remember, this guy, Marconi, was far better. He was a very, very, how to say that, publicity stunt guy. He could gather a lot of people and showed something amazing. Anyway, so Rutherford gave up pursuing the research in communications and went back to particle physics and discovered the existence of nucleus and got Nobel Prize in, I believe, 1900. And interesting thing is that Marconi also received Nobel Prize in physics in the next year. So if you remember the history of Nobel Prize, there were some people, very few people, who was not a scholar, professor or some, but received Nobel Prize, not in peace, but in physics or something. So Marconi received Nobel Prize in physics, thanks to his contribution to the theory and practice of wireless telegraph. Anyway, so this period was amazing period. You can also see that even though, before Marconi started to replace wired telegram, it was not completely replaced. Bell, Alexander Graham Bell, invented telephone. And telephone is invented, wireless telegram is invented, then what would be the next big thing? Probably people who lived this time thought in that way. Okay, we have telephone, we have telegram, we have wireless telegram. What would be the next big thing? Wireless voice or wireless telephone. Okay, so a lot of people again moved that way. And very interesting thing is that, see that? Just in several years, first wireless voice was broadcasted over the Atlantic Ocean. It was very, very amazing thing. And then this technology at that time, very crude, was continuously refined. And first, the AM radio broadcasting was popularized, and then FM broadcasting, and even the television broadcasting was popularized. And we've been improving that a lot, actually. So now let's see some figures, because this kind of table is very hard to read. So if you visit a small town, but very old town in Canada or United States, you will see some information saying that historic buildings of our town. And usually those historic buildings include fire stations and telegraph station, because that was very important. Every information was handled here. So from telegraph station over town to the next telegraph station, there was a wire dangling over the sky. But if it is more than a few hundred meters, you needed what? A pole, right? currently, the proper word for that pole is a utility pole. However, what do we call that? 전봇대 or sometimes 전신주. Some of you have thought about why this pole is called 전봇대 or 전신주. Now you understand. It was for 전보, telegram, right? Or telegraph. We still call 전봇대 as 전봇대. It's pole for telegram or telegraph, even though that does not convey any telegraph wire, does not have, right? So currently, these poles have what? The power, electric power cable, or some internet communication cables. Mostly communication cables in our country, KT, is under our ground. And even the power lines are now constructed underground. But anyway, so this 전신주, 전봇대 still conveys this old history. Anyway, here, this is a very old, probably 1950 something, Seoul Tower. And you see something here. And this is called a key, okay? So pushing this button is called keying. Okay? By keying, what do you do usually? You send a Morse code. So when the wired telegram was commercialized, these stations have several operators, not only one, but also several operators who could send this message Morse code using by keying very fast. And also they could, by listening to the sound, because it was connected to a loudspeaker, they could hear do something like that, and could immediately understand and write the message. Interestingly, some famous engineers or inventors, their first job was an operator in the telegraph station. For example, you know the Thomas Edison, one of the greatest inventor and one of the greatest showman. Probably you have to remember this way. The Marconi, Edison, and Wright brothers were very, very interesting people. Even though one brother of Wright brothers was very shy, but the other was very interesting guy. Anyway, they were far better than Steve Jobs. We just didn't see what they were doing or performing long ago, because we are living in a different time. But anyway, so Thomas Edison, when he was very young, was hired as an operator in the telegraph station. And this guy, even though he was kicked out from elementary school, he was very, very clever. And he could key the key very, very fast. So when he was moved to, he was kind of scouted from a small station to big station, those operators, the senior operators, assigned him to a line in where the other side, there was a very fast operator. And they wanted to kind of frustrate Thomas Edison. And what happened? Actually, the guy on the other station got frustrated because Thomas Edison was so fast. So even though he was an elementary school dropout, it seems that those dropouts are very interesting guy, right? Steve Jobs was a dropout, and Bill Gates was a college dropout, and even we have an elementary school dropout who was a very famous inventor. Anyway, so this is a telegraph station. This is the key. And this word is very important because if you take a digital communications course, you will see the word keying again and again and again. And the origin is this one. Origin is the key in the wired telegram. And also, this is a very interesting thing. So the story is like this. After today's class meeting, in lunchtime, you meet some of your other friends who is not taking this course and ask them, hey, why do we call 전봇대 as 전봇대? Probably many of them never thought about it. Got it? Anyway, so this is James Clerk Maxwell. And this is a picture from Wikipedia showing electromagnetic wave. Here on this page, I want to emphasize this one. You have to differentiate 전자기파 from 전파. Some people believe 전파 is an abbreviation of 전자기파 by dropping these two words. Actually, it is not. Okay, the translators in the Meiji era of Japan, they were very, very careful. So from electromagnetic, they converted this electro part as 전 and magnetic part 자, and they used the strange word key and wave, right? And according to Maxwell's equation, theoretically, from 0 Hertz to infinity Hertz, the electromagnetic wave may exist. And a specific part of electromagnetic wave, lower part actually, is called radio wave. And radio wave, they translated to 전파. Got it? However, 99% of Koreans just cannot distinguish these two. But some of them, especially communication engineers, distinguish these two. So when you want to talk about radio wave, mention it as 전파. Got it? If you want to talk about electromagnetic wave, use the term 전자기파. Got it? So this is an interesting phrase from my early undergraduate experience. So when I was taking a course, professor talked about 전파 특성. And I thought he was stuttering at that time. But actually, it was not. What is that? This is radio wave. And this is what? Propagation. So he could just spoke, so he could write down the Chinese character. So, but this 전파 is actually this one. And this 전파 is actually that one. Okay, so 전파 특성 means radio wave propagation characteristic. Got it? So be careful. Now, this is the figure from Alexander Graham Bell's patent, I believe. Very interesting thing. And here goes another episode, and I hope you have one of your important lessons. So let's think about a telephone. And let's try to understand what it is. One of the ways to understand something is to what? Divide into smaller elementary component and try to understand each elementary component and then combine little bit and try to understand the entire, for example, wood, right? So if we divide or dissect this so-called telephone, as you can clearly see here, it consists of two things. One is what? So-called speaker or loudspeaker. What is the other one? Microphone. So simply put, a telephone is a simple combination of two things, microphone and loudspeaker. of course, from microphone to the other side where a loudspeaker is connected, you have to amplify the signal. But people never say that Alexander Graham Bell invented an amplifier because it was already there. Actually, microphone was invented by other people and existed already. Loudspeaker was invented by other people already. Amazing. But no one could make it work as a single system. And you know, the Alexander Graham Bell's background was not engineering. He was a doctor, I remember, right? So he could combine already invented systems and could patent it. And this type of patent, combining already existing inventions, is called a mashup patent. And interesting thing is that if you apply a patent by combining what are already existing, usually your application is rejected. Because this addition of inventions is not recognized as a novel invention. However, no one could do this, interestingly, at that time. So Alexander Graham Bell submitted his invention and got it through the Office of Patent Office for the first time. So he could be remembered or celebrated as the inventor of telephone. This is Heinrich Hertz portrait. And by using this equipment, these two equipments, he could demonstrate existence of electromagnetic wave, whose existence predicted by Maxwell. And as you can see here, with this apparatus is figured here. As you see here and there are small metallic spheres. These are metallic spheres. Connected to, of course, conductor. And there is a small gap, very small gap. So this, and afterwards, when this receiver, very simple passive equipment, is exposed to electromagnetic wave, what happens? Current, actually voltage accumulates, and suddenly the insulation is broken. Insulation by air is broken, and you can see what? A small thunder, right? Called spark. So this is called a spark gap. And spark gap shows spark. So, for example, if I place the transmitter here and receiver there, and I just operate the transmitter only, but all of you can see what happens when I push the switch on the transmitter. You see a spark on the receiver. In that way, Heinrich Hertz could demonstrate the existence of electromagnetic wave. Interesting thing is that he was a professor in Germany, I believe, and he showed it. Hey, people, I've successfully demonstrated the existence of electromagnetic wave. And of course, at that time, newspaper reporter asked him, so what's the use of it? He said that, well, I just show the existence. It may not have much application. So professors, many professors are professors. They just want to advance the theory. But what happened? This news spread a lot. And this guy, same people, same person, Marconi. At that time, he was in Italy. By the way, the Italian museums, historical museums, talks, I remember two people as a very famous Italian. One of them is always Marconi. That's what I heard. But anyway, this guy was very well educated in some sense. he was very smart and very ambitious. So when he heard about the possible existence of electromagnetic wave and also the successful demonstration of electromagnetic wave, he just thought about replacing wired telegram by wireless telegram. Of course, he was not the only person. The idea was very simple. Okay? There is a wave called electromagnetic wave, and it's very fast, and it could reach very far away. And now you have a lot of utility poles covering entire Italy at that time. And probably as a Marconi, you have thought about it. Okay, what if we could remove all the poles by using this new wave to convey the Morse code? So he started to experiment. Actually, he was very, very quick. He could transmit Morse code around 100 meters around his home, kilometers. The problem was that when he submitted some application to Italian government, especially for military communication, the generals, probably very old and fat, just ignored him. So what did he do? For example, if you were him, what would you have done? Just frustrated? No. Marconi moved to United Kingdom, Britain. At that time, London was kind of San Jose in this time. So there was a kind of, how to say that, money valley, not Silicon Valley at the time, industry valley. There were a lot of bankers. All of the world money was traded there. There was stock market and a lot of investors who was hunting for something new. And Marconi moved to England. And then he could successfully raise the fund to continue his research. He hired a lot of smart engineers. He could demonstrate something new every month. And he got the Nobel Prize, interesting. Anyway, so, okay, I was mistaken. It was 1909 Nobel Prize. Okay, anyway, and he was also a very lucky person. One of the reasons why I put this figure is that he kind of sent his operator over the Atlantic Ocean and asked him to transmit some message on a specific date and time. He didn't even check whether it works or not, but he asked the newspaper reporters to come. Hey, I'm going to demonstrate transatlantic wireless telegram on, for example, September 5th, 9 a.m., something like that. And he just collected the reporters without knowing whether it works or not. And the day has come, and people on the newspaper, a lot of scholars, professors probably in physics and electrical engineering, predicted it will fail. They computed the transmission power in, for example, London or some coastal area in England. And it's not that difficult to compute the received power over the Atlantic Ocean. And due to this curvature of Earth and attenuation due to the air, moisture, they predicted it will definitely fail. So it's like, think about that. Steve Jobs says that, okay, we are going to show you a new iPhone tomorrow. And most of the professors in the world says that that's not possible. What will happen? You are very interested, right? Hey, what will happen? And he was successful. So every so-called clever people got a lot of shame. Why? Because there existed a reflector we didn't know at that time called ionic sphere, ionized layers of plasma that reflected the signal. And also, ocean has reflection. So he could successfully demonstrate transatlantic wireless telegraph. He was a very, hardworking person, and he was a very lucky person too. And what is one of the lessons from this episode? If you work hard, you can be also lucky. Okay, try a lot, and you could be lucky. Amazing. Anyway, another interesting thing is that between these two, there is a history about radar. And radar, that is the abbreviation of radio ranging and detection, is to use radio wave to find the distance of a target and the presence of a target and even the speed of the target. And interestingly, immediately after the wireless telegram was invented, even Marconi himself reported that the radio wave could be used to detect something, presence of something. So when the World War II especially started, the Allies and Axis intensively used this new equipment to win the battle. And the British guys, as I told you, the most advanced radio engineering was kind of performed in British. And some of them was started to moving to the US. So what do you guess? These British guys had very, very advanced radar system. A German didn't have. US radar system was much better than Japanese radar system. So the British guys could successfully deter any possible invasion of German force over the strait. And also the US Navy could easily position the Japanese Navy and could win the Pacific War. Anyway, and after the World War II, here goes one important date. Claude Shannon, he was an electrical engineer. Actually, he got his bachelor's degree from University of Michigan in electrical engineering. And he double majored mathematics. And probably he had interest in probability theory a lot. And he moved to MIT for his graduate study. And he published two theses. For the master's thesis, he invented kind of the and, not, or, those simple operation could do almost everything for our future electrical engineering. And then in his PhD study, he wrote a mathematical theory of communications that not only includes data compression, data transmission, and security in communications, but also talked about a lot of other stuff. And let me skip a lot. Our human beings invented the internet and the Ethernet and Wi-Fi, cellular system, and satellite communications. And we are living in what? Now, the world of information and communication. So this is a short history of electrical communication. And when I was at your age, there was an interesting professor in our department. And he was very interested in this key. So he thought about this. What would be the next big thing in communication? And probably he reviewed the history of electrical communication, and probably he paid attention to this. Okay, so suppose I'm living in late 1800s, and people have found a new wave called electromagnetic wave, and that can propagate far away. And if I put some message on that wave, then now I have a new communication method, right? And he was very, how to say that, oriental key obsessed professor. 알죠, 여러분들? 기를 이용한 뭐 이런 거. 네. So he believed the existence of key. And as a communication engineer, he wanted to use combined communications technology using this key. And after he retired, actually he was at that time almost retired, he was kind of scouted by the Korean Key Association. Probably a lot of misbelieving people, myths here, believing people were members. And interestingly, I still remember, they found a girl who could read the textbook without even opening the book. And as a chair of the Key Association, actually, he gathered a lot of news reporters because he was a professor of Seoul National University. So he could kind of use his fame to ask the reporters to come. And actually, a lot of people has come, and they demonstrated the girl could read the textbook, randomly selected, not just from a finite choice, but randomly chosen from some of the attendees. I don't know whether it has been orchestrated already, but anyway. But unfortunately, there was no progress after that. I'm not sure whether we have new breakthrough like the discovery of the existence of new wave, like electromagnetic wave, but we don't know, right? Yeah, there are a lot of things we don't know. Anyway, so far we covered the history, and let me move to this one. So I will talk about some important concepts in satellite communications because you guys have more and more interest. So first thing is that what is a satellite? There is an artificial satellite and natural satellite. We talk about natural satellite. And probably you know the first satellite launched by the Soviet Union. They were very proud of it at the time. The communists are very proud of that. They were the first group. And when the Sputnik was going around the Earth, it just was a radio transmitter. They put a radio transmitter there, but there was no message. It just periodically sent beep sound after demodulation. So it was a kind of beeping metallic chunk. Interesting thing is that when the US engineers first heard that sound, they immediately thought about the use of artificial satellite as a communication system. So one of some first artificial satellite of the United States was called ECHO. And it was a huge balloon, actually, of very thin metallic material. It was kind of folded inside the payload. And when it reached the orbit, the compressed air was pumped in. And I remember its diameter was more than 10 meters. And the surface was metallic. So it could reflect the radio wave. Now, we have very, very sophisticated satellites that have electrical systems. So when they receive the uplink signal, this is called uplink, and this is called downlink. And you must pay attention to the arrow. When it receives uplink signal, it amplifies and shifts the carrier frequency and retransmit downwards. That is called a bent pipe communication satellite. So it's similar to the pipe that is bent, right? So your signal comes in and through the bent pipe, it goes down. But actually, it's more than bent pipe. As I told you, if a bent pipe satellite receives the signal, it amplifies and also frequency translates and then retransmits. Another satellite is so-called an onboard processing satellite. What is that? It receives the signal, it demodulates, and even sometimes detect the symbol and re-encode and even change the waveform and then retransmit. Most of the communication satellites are, they say, bent pipe satellites. Even though it is a very dumb satellite communication satellite, it is also very versatile. You can just change ground station's configuration and it just amplifies and forward. What happens? You find, hey, something wrong in our algorithm for an onboard processing satellite. You have to yourself go there, or in these days, you can modify in softwareize. But anyway, so bent pipe satellite is very versatile and useful, but onboard processing satellite could be also very useful when, for example, uplink signal is very weak. In that case, just amplifying and forward may just add the noise or interference, but onboard process satellite may remove interference, for example, from enemy signal. So there are two types, widely speaking, two types of satellite, according to the what is on the payload. This classification is by the height of orbit. So GEO is from geosynchronous satellite. You know what does that mean, right? So on the equator of the celestial equator, if it is placed in some specific height altitude, then its period is same as our Earth's rotation period. In that case, the satellite appears to be stations in a same position. That is called geosynchronous satellite. However, that distance is very far away. It's more than 36 kilometers from the surface. So our uplink transmission power must be very large. And some applications may not allow that. So people try to have lower Earth orbit, and this is medium Earth orbit. Okay, so here, this is medium Earth orbit. And these days, for example, SpaceX's Starlink satellites are LEO satellites, low Earth orbit satellites. And their altitude is very, their orbit is very small, just a few hundred kilometers from the surface, something like that. And something interesting is that long ago, only a satellite operated alone, but these days, thanks to SpaceX, satellites work together. They even have so-called inter-satellite link. Especially they use laser or infrared. So suppose this is us and here is the Starlink satellite. They can communicate each other. So for example, in the uplink, you receive a radio wave, you convert it to a laser, the visible optical signal, and relay to the other satellite, and then it converts back to radio wave and send it to downlink, something like that. And as you know that in the orbit, there is no air. So this optical link may be very, very useful. And not only satellite, you can use airplane or some airship or drones for the communications. So these days, not only this land mobile or terrestrial network, people want to extend our network to non-terrestrial. So in the next generation cellular communication system, people want to combine, put every possible communications together in a cellular communication system so that you can use your cell phone for satellite communications. The problem is that so far, this land mobile or terrestrial network has been separately developed from non-terrestrial network. And the ITU, the UN organization who kind of governs all the regulations, worldwide regulations on radio communication, they have been traditionally discussing these satellite communications separately from land mobile communications. So there are a lot of hurdles for the sixth generation cellular communication to combine these all. So probably in a few years, you will see that, okay, 5G is doomed, so let's move to 6G. And there would be a lot of advertisements saying that there is a satellite, or something like that, but that could be also a lot of exaggeration. As you've seen from 5G advertisement, where Son Heung-min just kicks a ball in London, and a student, a kid in Seoul, just kind of receives the ball in 3D hologram through 5G, and that never happened. So nobody knows. About the frequency bands, I covered this. I will cover in the next thing. Okay, the last topic is this one today. So in our electrical communications, I will mostly talk about radio communications because that is the center of electrical communications now. And you have to remember this one. Okay. In free space, it's a simple wave. However, we are not living in free space. We are living on the surface of the Earth. And this space is filled with so-called air. And air is composed of different molecules. And these molecules interact with our radio wave. So even though we have a line of sight from transmitter and receiver, we may have attenuation due to the molecules, oxygen, water, and some other CO2 or N2 or something. So never forget this one. Also, sometimes if it rains, we have a lot of trouble. Anyway, so as you see from here, there, you see some equations you've seen in signal gen systems. So be prepared. In order to review signal gen systems material a lot, in order not to be frustrated in next week. Okay, that's all for today.